I want you to do something for me right now. Just look at your wrist or check your phone. And I want you to imagine a clock, a standard analog 24-hour clock.
Right.
Now visualize that this clock represents the entire history of our planet, Earth. From the violent moment it coalesced out of cosmic dust, right up to this exact second where you're listening to my voice.
It's a classic analogy.
Yeah.
But honestly, it really is the only way to genuinely grasp the sheer scale of deep time we're dealing with today. Midnight is the birth of the planet, 0-100 hours.
Right. Midnight is the absolute start. Now, playing the odds here, if I walked out onto the street and asked a random passerby, hey, on this 24-hour clock, when does the interesting stuff happen?
The stuff people actually know about.
Exactly. When do humans show up? When do dinosaurs appear? When do we get the first animal that actually has a skeleton? Where do you think they'd place that on the dial?
Usually people guess around noon. Maybe they're generous and say 6 p.m. But if you're looking for the familiar landmarks, the T-Rex, the woolly mammoth, the trilobites, you are waiting until very late in the evening.
Very late. We are talking about the last hour or so. Actually, dinosaurs don't even show up until about 11 p.m.
Yeah.
And humans, we're the last few seconds before midnight. We're practically a rounding error on the clock.
A very noisy rounding error.
Fair point. But today we're not talking about that last hour. We are doing a deep dive into the other 23 hours, the hidden majority of time. We are talking about the Precambrian Superion,
which covers approximately 88% of Earth's history, roughly 4 billion years.
That number just, it breaks my brain every time I think about it. 88%. Essentially, if this deep dive covers the history of Earth, we're spending all our time talking about everything from midnight until about 10:45 p.m.
Exactly.
And what drives me crazy is that most history books, even science textbooks, they just skip this part.
They really do.
It's usually a single paragraph that says something like, Earth cooled, some slime grew, and then boom, Cambrian explosion.
It's a massive oversight, though, I mean, it is a forgivable one given the lack of obvious fossils. Okay. But the mission of our discussion today is to correct that. We aren't just going to list dates and Ross formations. We need to understand that this period, the Precambrian, is when the operating system of the planet was actually built.
I really love that framing, the operating system. Because without an OS, the apps, which in this analogy are the dinosaurs and, well, us, they just can't run.
It really is the perfect metaphor.
Yeah,
this is when the hardware was assembled. The core, the mantle, the crust, all of it differentiated.
It's when the foundation was poured.
Right. It's when the atmosphere was engineered, literally built from scratch by biological and geological processes working together. It's when the oceans were filled.
Yeah.
And most importantly, it's when life transitioned from simple chemical interactions to complex multicellular organisms. We are going from the formation of the planet about 4.6 billion years ago, right up to the doorstep of the Cambrian explosion, which is 538.8 million years ago.
So if this period is so foundational, why is it so mysterious? I mean, why do we know so much about the last 12% and so little about the first 88%? Is it just that nobody cares? Or is it that it's harder to find the clues?
Oh, it is definitely not a lack of interest. Geologists are completely obsessed with this era. It really comes down to rock record scarcity.
Right.
You have to remember, Earth is a very active planet. It is not like Mars or the Moon, which are geologically dead for the most part. Earth recycles its crust.
Like a giant conveyor belt.
Exactly.
Yeah.
Plate tectonics constantly subducts old rock, pushes it under the continents, and melts it down back into magma.
So the evidence is literally being destroyed. The library is burning itself down every few 100 million years.
Wow. That's exactly what's happening. Or if it's not totally destroyed, it's cooked.
Cooked.
That's metamorphism. Extreme heat and pressure alter the chemical signatures in the rocks. It's like taking a history book, throwing it in a fire, and then burying the ashes under a mountain.
Wow.
And for the rocks that do survive all of that, they're often buried incredibly deep underground. In places like Kansas, for example, the Precambrian basement rocks, the actual foundation of the continent, are buried beneath thousands of feet of younger sediment.
So you can't just walk up to a cliff face and read the history like you can in the Grand Canyon.
No, you can't. You have to drill for it.
It's like trying to read a book that's been shredded, burned, and then buried in a landfill.
A grim but highly accurate analogy. However, we have developed incredibly sophisticated tools to read those shredded scraps. We rely heavily on high-precision geochronology.
Right, and in the sources we're using for this deep dive, I kept seeing two acronyms pop up over and over. ID-TIMS and LAICPMS,
Yes.
which honestly, they sound like sci-fi weaponry, but I know they're important.
They are the absolute heavy hitters of modern geology.
Let's break those down a bit, because I don't want to just gloss over the how. What is ID-TIMS actually doing?
Right, so IDTIM stands for isotope dilution thermal ionization mass spectrometry.
Okay, that's a mouthful.
It is, but it's the gold standard for high-precision dating. Essentially, you take a mineral crystal, usually something very tough like zircon, you dissolve it completely in hydrofluoric acid, and you measure the ratio of uranium to lead with incredible, unbelievable accuracy.
Because uranium decays into lead over time, right?
Exactly. Because we know the exact half-life of uranium, how fast it decays, we can calculate the age of the crystal based on how much lead is trapped inside it.
Like an hourglass.
It's like an hourglass. And ID-TIMS is like using a scalpel. It gives you air margins of maybe less than 1,000,000 years on a rock that is 1,000,000,000 years old.
That is insane precision. That's like measuring the distance to the moon and being off by a few inches.
It's a marvel of modern chemistry.
And the other one, the LAICPMS.
Laser ablation inductively coupled plasma mass spectrometry.
Okay, laser ablation definitely sounds like a weapon.
It's a bit more aggressive, yes.
Yeah.
It's faster than ID-TIMS and allows for spatial resolution. What you do is you literally shoot a laser at a tiny spot on a crystal, we're talking microns here, and you analyze the dust that flies off.
So you're vaporizing a microscopic chunk of the rock.
Yes, and feeding that vapor into a mass spectrometer, it lets you map the age of different parts of a single crystal.
Why does that matter?
This is crucial because a single crystal might have a core that is 4 billion years old, but a rim on the outside that is only 3 billion years old. It shows the crystal grew in stages over 1 billion years.
So essentially, these are high-tech magnifying glasses that let us look at chemical signatures on an atomic level.
Precisely. They allow us to date microscopic crystals and analyze isotopic ratios to reconstruct ancient environments. We can tell what the air tasted like or how hot the oceans were just by looking at the chemistry trapped inside a crystal the size of a grain of sand.
That is just wild. It makes you realize that rocks aren't just hard things you trip over, they are actual data storage devices.
They are the ultimate hard drives.
Okay, so we have the tools. Let's fire up the time machine. We're going back to the very beginning. Midnight on the clock. The Hadean Eon.
The Hadean, named after Hades, the Greek god of the underworld.
Which definitely suggests it wasn't exactly a vacation spot. I've always pictured this era as a massive magma ocean, just volcanoes everywhere, lava seas, asteroids constantly falling from the sky. Is that an accurate picture?
For the very beginning, yes, absolutely. The period from 4.6 to about 4.0 billion years ago was incredibly violent.
Just chaos.
Complete chaos. You have the initial accretion of the planet dust and rocks clumping together under gravity in the early solar system. But the defining moment, the thing that really set the stage for everything that followed, was likely the Great Bombardment.
This is the collision with the planet they call Theia, right?
Correct. The leading hypothesis is that a protoplanet roughly the size of Mars named Theia slammed into the proto-Earth.
When you say slammed, are we talking a cosmic fender bender, or are we talking total planetary destruction?
Oh, we are talking about a cataclysm that very nearly destroyed the entire planet. The energy release was incomprehensible. It didn't just break rocks. It likely vaporized a huge portion of Earth's mantle.
Vaporized rock.
That's
I can't even process that. Rock turning into gas.
Imagine rock turning instantly into a superheated atmosphere of silicate gas. It threw a massive amount of debris into orbit around the Earth.
And that debris eventually became the moon.
Exactly, coalesced to form our moon. That's why the moon has a composition that is so strikingly similar to Earth's mantle.
Okay, that makes sense.
But for Earth itself, the impact meant a global magma ocean. The heat sources were just intense. You had the kinetic energy from all these massive impacts. You had gravitational compression squeezing the planet from the inside, and you had the radioactive decay of short-lived isotopes.
Like what?
Things like aluminum-26, which puts out a ton of heat as it decays.
So the floor is literally lava. The whole planet is a glowing ball of melt. What about the air? What are we breathing if we are standing on the shore of this magma ocean, assuming we don't instantly burn to a crisp?
Why you wouldn't want to breathe it. The first atmosphere was what we call hydride-rich. It was actually quite similar to the gas giants like Neptune or Uranus today.
So what's in a hydride-rich atmosphere?
Think methane, ammonia, and water vapor.
So it smells like rotten eggs and industrial cleaning fluid.
And it's incredibly dense.
Yeah.
Then, as the planet started to differentiate, meaning the heavy stuff sank to the core and the lighter rock floated to the top, and volcanoes started pumping out gas from the interior, the atmosphere shifted.
To what?
It became dominated by carbon dioxide, nitrogen, and water vapor, but absolutely no free oxygen. If you took a breath, you would asphyxiate immediately.
Sounds lovely. So the traditional view, the one I definitely learned in school, is that this hellscape lasted for hundreds of millions of years. Just a long, dark, molten nightmare. But reading through the research you sent over for this deep dive, there seems to be a major plot twist.
A massive plot twist.
Hmm.
This is known as the cool early Earth hypothesis.
Cool as in temperature, not cool as in, wearing sunglasses and a leather jacket.
No, temperature. We used to think the surface remained above the boiling point of water for a very long time. We basically assumed it took 500 million years for the crust to even solidify and cool down.
Right, because there's so much residual heat.
Exactly. But the physical evidence from the Jack Hills in Western Australia changed everything we thought we knew.
These are those zircons you mentioned earlier, right? The tough crystals.
Yes. Zircons are incredibly durable minerals. Zirconium silicate. They are ridiculously tough. They survive extreme erosion. They survive intense metamorphism. They are basically nature's time capsules.
Huh.
And geologists found zircons in those Australian hills that date back to 4.4 billion years ago.
4.4, which means...
That is only about 150 million years after the planet formed.
And what did that specific time capsule say? What was the big revelation?
It spoke of water, specifically the oxygen isotope signatures inside these crystals.
How does oxygen tell you about water?
We look at the ratio of oxygen 18 to oxygen 16, and the specific ratio found inside these ancient crystals showed that they had to have formed in the presence of liquid water.
Wait, just so I'm clear. 150 million years after the planet is a literal ball of vaporized rock and molten slag, we have liquid water.
That is the inescapable implication. It suggests the Earth cooled much, much faster than we ever thought possible. The surface temperatures must have dropped below 100 degrees Celsius, allowing the massive amount of water vapor in the atmosphere to condense and rain down to form oceans.
But hold on a second. You mentioned earlier that the atmosphere was incredibly dense, full of CO2 and nitrogen. If the pressure is super high, doesn't that change how water behaves? I mean, I know water boils at a lower temperature in Denver because the air is thinner there.
Exactly. And the physics works the other way, too. It's a pressure cooker effect.
Huh.
The atmospheric pressure back then was likely massive. We're talking around 27 atmospheres.
27.
Yes, that's 27 times the pressure you feel standing at sea level today.
So it's like being hundreds of feet underwater, just standing on the beach.
Right. And under that much atmospheric pressure, water doesn't boil at 100 degrees Celsius. It can stay liquid at temperatures way, way hotter than that, maybe 200 or even 300 degrees Celsius.
So we have these hot, high-pressure oceans. The research called them oases.
Yes, liquid water oases. And this is crucial because water is the universal solvent of life. These hot, high-pressure oceans were the potential laboratories for biology.
Setting the stage.
Exactly. They provided the necessary medium for prebiotic chemistry, the complex mixing of organic molecules that would eventually cross the threshold into life.
So barely out of the gate, while the clock is still just a few minutes past midnight, Earth is already trying to set the stage for life.
It wasted no time.
That brings us to the next chapter. The clock keeps ticking. We move from the Hadean to the Archean eon.
The Archean runs from about 4.0 to 2.5 billion years ago. This is where the Earth finally stops just melting everything and starts actually building a permanent crust.
This is where we get the first real land, like continents.
Not continents as we know them today. We get what are called greenstone granite belts.
Greenstone granite belts.
Right. These are essentially the deep altered roots of ancient island arcs and volcanic plateaus. Think of something geologically similar to the Japanese archipelago or Indonesia, but much, much more primitive.
So it's a bunch of volcanic islands.
Yes. We don't have massive, stable continents like Africa or North America yet. Just these buoyant, granitic proto-continents floating around on a very hot, very active mantle.
And the whole color palette of the Earth is changing here, right? We call this section of the deep dive the orange Earth. Why orange? Was the rock orange?
No, it was the sky. The sky was orange. And this brings us to a fascinating astronomical problem known as the faint young sun paradox.
I've heard of this. The sun was weaker back then.
Yes, Standard astrophysical models tell us the sun was about 25 to 30% dimmer during the Archean than it is today.
30% is a lot.
It's a huge amount.
And
Stars actually get brighter and hotter as they age because they burn through their hydrogen fuel, which causes their core to compress and heat up.
okay, so if the sun was that weak, shouldn't the Earth have frozen solid? If you turn down the sun's heat by 30% today, we'd be an ice cube.
Instantly, Earth would turn into a ball of ice. But as we just discussed, the geologic record clearly shows liquid oceans all through the Archean. We have rocks that could only form in liquid water.
So what kept us warm? A really thick atmospheric blanket.
Exactly, an extreme greenhouse blanket.
Yeah.
But not just carbon dioxide. The real hero, or villain, depending on your perspective down the line, was methane.
Methane. Like natural gas.
Yes, and this is where life enters the chat in a really big way.
Oh, so biology is making the methane.
Yes, we had methanogens. These are a type of archaeous single-celled organisms that absolutely thrived in these early oxygen-free oceans. They produced massive amounts of methane gas as a metabolic waste product,
And methane is a super powerful greenhouse gas, right?
much more potent than CO2. On a molecule-for-molecule basis, methane traps significantly more heat. Some modern estimates say it's 25 to 80 times more effective at trapping heat than carbon dioxide over certain time frames.
Wow.
This biological pump created a massive methane greenhouse. But here is the visual payoff. When you have that much methane interacting with sunlight in the upper atmosphere, it creates a complex organic haze.
A haze.
Very similar to what we see right now on Titan, the largest moon of Saturn.
So if I was standing on one of those volcanic protocontinents 4 billion years ago and I looked up, the sky wouldn't be blue? It would be a hazy, glowing orange.
Correct. A thick, organic orange smog. And that haze served a critical dual purpose.
It kept the heat in, solving the faint young sun paradox.
Right. But it also acted as a planetary shield. You have to remember, there is absolutely no free oxygen yet, which means there is no ozone layer.
Oh, right. So the surface is just getting blasted by UV rays.
Bombarded by lethal ultraviolet radiation. But the thick methane haze helped absorb and scatter some of that UV light, protecting the early life forms that were living in the shallow waters.
Talk about a perfect symbiotic relationship. Life produces the exact gas that keeps the planet warm enough and shielded enough for life to continue existing.
Coevolution is the absolute theme of the day here. Life doesn't just sit passively on the rock, it changes the rock. It fundamentally changes the air.
Speaking of life, let's look at the actual fossils. What are we physically seeing in the Archean rocks?
The star players are stromatolites.
Traumatic.
Yes. These appeared definitively in the rock record, around 3.5 to 3.7 billion years ago.
What do they look like? Are we talking about little shells?
No, if you look at them in a museum, they just look like lumpy rocks. Sometimes they're layered on the inside, kind of like an onion or cabbage, but they're actually fossilized microbial mats.
So a rock made of bacteria.
Layer upon layer of bacteria-trapping sediment. There were sticky, shallow water mats on the seafloor. Sand would stick to the bacteria, then the bacteria would grow up through the sand layer to get back to the sunlight, then more sand would stick. Over thousands of years, this process builds these distinctive rock structures.
It's not exactly the T-Rex of the Precambrian.
No, it's not Jurassic Park.
Yeah.
But it is the hard, physical evidence that life had firmly taken hold and was engineering its environment. But the real game changer, the biological innovation that would literally alter the chemistry of the entire universe, at least from our perspective, happened late in the era. In the Neo-Archean, around 2.8 to 2.5 billion years ago.
Let me guess. This is when they figured out how to use the sun. Photosynthesis.
Specifically, oxygenic photosynthesis.
Right, because there are other kinds.
Exactly. Bacteria had been doing simple photosynthesis for a while using things like hydrogen sulfide to get electrons, but cyanobacteria, which are often called blue-green algae, they figured out how to use sunlight to split water molecules, H2O.
They broke the water apart.
Yes. And the metabolic byproduct of that neat little evolutionary trick was free oxygen, O2.
Okay, so this is the moment everything flips. Cyanobacteria start pumping out oxygen into the water. But in the sources we reviewed, there's a really specific note about a delay.
A massive delay.
Right. If they're making all this oxygen, why didn't the atmosphere just fill up with it right away?
Because the oceans were absolutely full of iron. Dissolved ferrous iron, A2 plus eel.
Iron in the water, like a rusty pipe.
Well, dissolved iron is actually clear. You wouldn't see it, but there was tons of it constantly being sourced from underwater hydrothermal vents. Now, what happens when you introduce free oxygen to iron?
You get rust.
Exactly. As soon as the cyanobacteria puffed out a little bit of oxygen, it immediately reacted with the dissolved iron in the water and precipitated out as solid rust.
Iron oxide.
Yes, minerals like magnetite and hematite. This solid rust literally rained down through the water column to the ocean floor.
And that raining rust is what we see in the rocks today.
Yes, it formed the banded iron formations, or BIs for short.
I've seen pictures of those. They're stunning.
They are beautiful rocks. They have alternating stripes of deep red iron-rich layers and gray silica-rich chert layers. These geologic formations are essentially the fossilized evidence of a billion-year chemical war.
A chemical war between oxygen and iron.
The ocean was acting as a massive buffer, a giant chemical sponge. It soaked up virtually every single molecule of oxygen produced by the cyanobacteria for hundreds of millions of years.
That is just a staggering thought. The bacteria are working overtime, day and night, pumping out this gas, and the ocean is just chemically eating it all up, turning it into heavy red rock.
Until the sponge finally got full.
And that leads us perfectly into section 3 of our deep dive, the Paleoproterozoic. The iron sponge in the ocean is completely full, no more room. What happens?
The oxygen catastrophe.
Oh.
Or, if you want the more formal, polite scientific term, the Great Oxidation Event, which started right around 2.5 billion years ago.
I honestly prefer oxygen catastrophe, or even oxygen holocaust, as I saw one paper call it. Sounds much more dramatic. But it really was a mass extinction, wasn't it?
It was almost certainly the single greatest extinction event in the entire history of the planet, though of course we don't have the macroscopic fossils to count the bodies.
Because it's all microscopic.
Right. But you have to understand the biochemistry here. For the life that existed everywhere back then, the strict anaerobes oxygen was a deadly poison. It was highly toxic.
It burned them.
Chemically, yes. It fried their delicate cellular machinery. Free oxygen causes severe oxidative stress, actively destroying DNA, RNA, and proteins.
So the cyanobacteria basically polluted the entire world with their toxic waste product, which just happened to be oxygen, and killed almost everyone else.
Pretty much. They terraformed the planet completely by accident. The oceans and then the atmosphere flooded with a toxic gas. But, as with almost all crises in Earth history, it drove incredible evolution.
The survivors.
Yes. The survivors were the specific microbes that randomly developed antioxidant enzymes to protect themselves. Things like superoxide dismutase, which neutralizes the toxic effects of oxygen.
Okay, so they built a defense mechanism.
And even more importantly, some of those survivors took it a step further. They didn't just tolerate the oxygen, they learned to use it.
Aerobic respiration.
Exactly. It's like switching from a low-grade fuel to high-octane rocket fuel. Burning food molecules with oxygen yields way, way more cellular energy than any of the old anaerobic methods.
It's just vastly more efficient.
Unbelievably more efficient. This massive leap in available energy is what eventually, way down the line, allowed life to get big and complex. You don't get animals without aerobic respiration.
So oxygen is fantastic for the future of complex life, but I see in our outline here that it was disastrous for the climate. We go from the warm orange Earth to Snowball Earth.
Yes, the very first Snowball Earth event. It's called the Huronian glaciation.
How does releasing oxygen cause a global ice age?
Remember the methane greenhouse we talked about? The thick orange haze that kept the planet warm under the faint sun?
Yeah, the methanogen blanket.
Well, oxygen is highly reactive. When free oxygen flooded the atmosphere, it reacted with that methane and essentially destroyed it. It oxidized the methane, turning it into carbon dioxide and water vapor.
But wait, carbon dioxide is a greenhouse gas too.
It is, yes.
Yeah.
But remember, methane is 25 to 80 times stronger. So as the oxygen stripped away the potent methane blanket and replaced it with much weaker CO2, the thermal retention of the atmosphere collapsed.
It's literally like someone pulled the heavy down duvet off the bed in the middle of winter and just left a thin sheet.
And the global temperature plummeted. We have solid geologic evidence of massive ice sheets reaching all the way down to the tropics. The entire planet may have frozen over completely for millions and millions of years.
That is genuinely terrifying. Just a silent, frozen white ball floating in space. How did life survive that deep freeze?
It was a near thing, but it probably survived in small, isolated pockets, maybe near active underwater volcanoes or in deep water refuges where liquid water persisted. But the planet was locked in ice and the recovery was incredibly slow.
How does it eventually thaw?
It took millions of years for volcanoes, which keep erupting even under the ice, to pump out enough fresh CO2 to gradually build a new, thicker greenhouse blanket and finally melt the ice.
But when the ice did eventually melt, the world had a brand new feature, right? The outline calls it the silver lining of the oxidation event.
Yes, the ozone layer.
Finally, some protection.
Exactly. The intense UV radiation from the sun hit those brand new oxygen molecules O2 high up in the upper atmosphere. The energy split the O2, and the free oxygen atoms recombine to form ozone, which is O3.
And that blocks the UV.
It acts as a phenomenal natural sunscreen. It finally made the surface waters and eventually the dry land itself safe for widespread colonization. Before the ozone layer, you had to hide deep underwater or under a rock to avoid getting your DNA fried.
But now the shallows are open for business.
The whole surface becomes habitable.
So we have oxygen, we have ozone, the ice is melted, the sun is shining, we are totally ready for some evolutionary action. And then we hit the boring billion.
Oh, yes, the Mesoproterozoic era, spanning from roughly 1.6 to 1.0 billion years ago.
Why do scientists call a billion years boring? I mean, that seems kind of rude to a billion years of history.
It is definitely a bit of a branding problem for that era.
Yeah.
Geologists can be harsh critics, but chemically, the name actually fits perfectly.
How so?
If you look at the carbon isotopes from this period,
I see.
specifically the delta carbon-13 signatures in the rocks, they are just a flat line.
No spikes.
Zero drama, no big jumps, no dramatic crashes, no giant glaciations to speak of, no massive tectonic shift.
It was just perfectly stable.
Extremely stable. We had an enormous supercontinent at the time called Columbia, which is also sometimes called Nuna, and it just stayed together for a very long time. It was an unprecedented period of tectonic stasis. The planetary thermostat was perfectly balanced.
But the ocean itself was pretty nasty, right? I have the stinky sea highlighted in my notes from the reading.
Yes, the Canfield Ocean model. We believe the ocean was deeply stratified during this billion years.
Stratified meaning layered.
Right. The surface layer had some oxygen, thanks to the cyanobacteria working away in the sunlight. But the deep ocean was entirely anoxic, meaning no oxygen, and it was sulfitic.
Sulfitic, meaning sulfur, like rotten eggs again.
Exactly. High concentrations of hydrogen sulfide gas dissolved in the deep water. It was highly toxic to most things. But the real structural problem for life was what that sulfur did to the available nutrients.
The sources called this the nutrient break.
Right. Life needs trace vitamins, essentially. It needs trace metals like molybdenum, copper, zinc, and iron. These metals are absolutely required to build the complex enzymes that life uses to do advanced chemistry.
Like what kind of chemistry?
Well, for example, nitrogenase. That's the specific enzyme used by microbes to fix nitrogen from the air so they can use it to build proteins. Nitrogenase physically requires specific metal clusters to function.
Okay, so they need the metals. What's the problem?
In a highly sulfitic ocean, those dissolved metals strongly bind with the sulfur and precipitate out as solid minerals. They basically fall like dust to the seafloor and get locked away in the deep mud.
Oh, I see. So the ocean literally ran out of vitamins.
Exactly. The biological evolution of complex forms stalled out because life just didn't have the metallic building blocks it needed to construct the complex cellular machinery required to get bigger. It was a billion-year nutritional plateau.
I mean, you can't have a billion years with absolutely nothing happening. There must have been some kind of underground movement, something brewing.
Oh, there absolutely was. While the geology was boring and the size of life didn't change much, the internal biology of life was making a massive foundational leap. This is when eukaryotes firmly established themselves.
Eukaryotes, those are our direct cellular ancestors, the cells that actually have a distinct nucleus holding the DNA.
Yes, and mitochondria. These are complex, powerful, highly structured cells.
How did they get so complex?
The leading theory is endosymbiosis. Essentially, one simple bacterium swallowed another simple bacterium, but instead of digesting it for food, they somehow formed a permanent partnership.
A microscopic alliance.
A very successful one. That internal bacteria became the mitochondrion, the energy plant of the cell. And that dedicated energy source gave eukaryotes the sheer power they needed to eventually grow and specialize.
Incredible.
And somewhere right in the middle of this so-called boring billion, roughly 1.2 billion years ago, these eukaryotes invented something very, very popular.
Sexual reproduction.
Yes. And from a purely biological standpoint, it is the ultimate evolutionary accelerator.
Because before sex, microbes just clone themselves, right?
Exactly. They just split in half. Asexual reproduction. If you had a beneficial mutation, maybe it passed on to your clones, but it was a very slow, linear process to adapt. But with sexual reproduction, you are actively shuffling the genetic deck every single generation.
You're mixing traits from two different parents.
You're creating massive genetic variability, and this variability allowed life to adapt much faster. which was likely crucial for surviving in the incredibly nutrient-poor, stressful Canfield Ocean.
So the ocean was boring, they had no vitamins, so they invented sex to survive. Makes total evolutionary sense.
It worked. And by the end of this era, we also start seeing the very first multicellular eukaryotes in the fossil record.
Really? What were they?
An organism called Bangiomorpha. It's an ancient type of red algae. It's the first definitive time we see differentiated cells physically working together in a complex, multi-celled structure.
So if we go back to our operating system analogy, the software was quietly being completely updated during this time. The hardware, the Earth itself, was stable and boring, but the biological operating system was getting a massive, fundamental overhaul.
Precisely. The code was being rewritten. And that overhaul happened just in time, because the long period of tectonic stability was about to abruptly end. The boring billion crashes hard into the Neoproterozoic era.
Section 5 of our deep dive, Chaos Returns and Snowball Earth makes a sequel.
The Neoproterozoic. This kicks off roughly 1.0 billion years ago, and it starts geologically with the dramatic breakup of a massive supercontinent called Rodinia.
Rodinia, I just love the names geologists give these supercontinents. Why did the breakup of this specific landmass cause so much global chaos? Continents break apart all the time.
It's all about its specific geographic location. Rodinia was unique because it was sitting almost entirely at the equator, straddling the deep tropics.
Okay, so it was hot.
Hot and wet. When tectonic forces finally ripped it apart, it created a massive amount of brand new coastlines right in those warm, highly active tropical zones. Yeah. This sheer increase in exposed, wet rock led to an explosion of chemical weathering.
I need you to unpack that for me. Chemical weathering. How does rain falling on tropical rocks fundamentally change the entire global climate?
It's a mechanism called a silicate weathering feedback loop. It's essentially the Earth's long-term thermostat. Rainwater naturally absorbs a tiny bit of CO2 from the atmosphere as it falls, which makes it slightly acidic, carbonic acid.
Right.
When that slightly acidic rain hits exposed silicate rocks on land, a chemical reaction occurs that essentially pulls that carbon right out of the air. The carbon binds with minerals, washes down the rivers, and ends up in the ocean, where it eventually precipitates out and gets locked away on the seafloor as limestone.
So the rain is literally scrubbing carbon out of the sky.
Exactly. And because the shattered pieces of Rodinia were all in the tropics, where it rains constantly and the heat accelerates chemical reactions, this weathering pump was just working overtime. It aggressively scrubbed the atmosphere of its CO2 greenhouse.
The planetary blanket gets violently pulled off yet again.
And this time, the resulting freeze was even worse than the Huronian glaciation we talked about earlier. We entered what's called the Cryogenian Period, the big freeze. We know of at least two absolutely massive glaciations during this time, the Sturtian and the Marinoan.
How bad are we talking here? Give me the visual.
We are talking solid ice from pole to pole. The entire planet looked like Hoth from Star Wars, a brilliant white sphere.
Solid ice even at the equator, like the deep tropics were frozen.
That is what the physical evidence tells us. Geologists find what are called dropstones in specific rock layers.
What's a dropstone?
It's a chunk of rock that gets picked up by a moving glacier on land. The glacier flows out over the ocean, breaks off as an iceberg, and floats out to sea. When the iceberg eventually melts, it drops that out-of-place rock straight down into the fine marine mud on the seafloor.
Like dropping a boulder into a puddle of clay.
Exactly. And we find these distinctive dropstones in rock strata that paleomagnetism proves were located perfectly at the equator at the time they were deposited.
Wow.
Think about the implication. Imagine an iceberg floating past a tropical beach, except there is no tropical beach.
Yeah.
Just more endless ice.
That's pretty definitive proof. If you've got massive icebergs dropping boulders at the equator, the whole place is frozen solid.
Yeah.
But you mentioned something in the notes called albedo feedback. That's the mechanism that makes it run away, right?
Yes. It's a brutal, simple physics loop. Albedo is just a measure of reflectivity. Ice is bright white, so it has a very high albedo. It reflects incoming sunlight right back out into space instead of absorbing it as heat.
Makes sense.
So the more ice that forms at the poles, the more sunlight gets reflected away. The Earth absorbs less heat, so it gets even colder, which means the ice spreads further toward the equator.
It feeds itself.
It's an unstoppable loop. Models show that once the advancing ice caps reach a certain critical latitude, around 30 degrees north and south of the equator, the feedback becomes totally runaway. The Earth just abruptly snaps into a fully frozen, totally glaciated state.
So how did life not just die entirely? If the entire global ocean is covered in a mile of solid ice, there's absolutely no sunlight penetrating for the cyanobacteria to do photosynthesis. The food web should completely collapse.
It was an incredibly close call. Life nearly ended, but it persisted by retreating into what we call refugia.
Tiny safe zones.
Yes. Think of deep-sea hydrothermal vents, where geothermal heat provides warmth and chemical energy completely independent of the sun. Or perhaps areas called polynyas.
Polynyas.
They are localized patches of open ocean water, kept from freezing over by intense wind patterns or strong upwelling currents. Or even just tiny, slushy meltwater pools sitting on the very top of the equatorial glaciers, hosting hardy communities of extremophile algae.
So life is just huddled in these tiny, isolated bunkers for millions of years.
Exactly. And that extreme geographic isolation is a uniquely powerful evolutionary force. Biologists refer to it as bottleneck and flush evolution.
Bottleneck and flush.
Right. The global populations are brutally squeezed, bottlenecked into these tiny, disconnected refugia. The environmental stress is immense, forcing them to evolve rapidly or die. Then, millions of years later, when the ice finally melts, they flush out and explosively colonize an entirely empty world.
So the Snowball Earth wasn't just a freezer, it was a high-pressure forge for evolutionary novelty.
Without a doubt. The most complex life forms emerged because of the disaster, not in spite of it. The stress demanded innovation.
But wait, how do you actually melt a Snowball Earth? If the bright white ice is reflecting all the sun's heat away, how do you ever get warm enough to break the cycle? It seems permanent.
It would be permanent if the Earth was geologically dead. But plate tectonics doesn't stop just because there's a shell of ice on top.
Yeah.
Volcanoes keep erupting right through the ice, constantly spewing carbon dioxide into the air.
Okay, but won't the rain just scrub the CO2 out again like before?
But there is no rain. The ocean is frozen, so there's almost zero evaporation. No water vapor means no rain. And because the continents are buried under a mile of ice, there is zero exposed rock for chemical weathering.
Oh, I see. The scrubbing mechanism is totally turned off.
Exactly. The thermostat is broken. So the volcanic CO2 just continuously builds up in the atmosphere, unhindered, for millions of years.
How high did it get?
We estimate that atmospheric CO2 levels reached staggering heights, maybe 100 to 1,000 times modern levels.
That is a wildly intense greenhouse effect.
And eventually it hits a breaking point. The sheer power of that ultra-greenhouse effect finally overpowers the reflective albedo of the ice. Once the ice starts to melt at the equator, the dark ocean water is exposed.
Which absorbs heat instead of reflecting it.
Right. And the loop works in reverse. It's a runaway warming event. And the melt, when it finally happened, was unimaginably brutal. It was geologically instantaneous. It might have taken only 2,000 to 10,000 years to completely melt the entire frozen planet.
From a deep freeze to a planetary sauna in just a blink of an eye.
The physical result was utter chaos. Massive global acid rain as all that CO2 interacted with the new water vapor, giant superstorms, and this intense chemical storm created what we call cap carbonates.
Cap carbonates? What is that?
If you look at the rock record from this exact boundary, you see a thick layer of messy, jumbled glacial rubble rocks scraped up by the ice. And then, bam, a razor-sharp line. Sitting directly on top of the rubble is a thick, distinct layer of limestone. That limestone is the physical manifestation of the atmosphere, rapidly dumping millions of years' worth of accumulated CO2 back into the recovering ocean as the world dramatically heated up. It capped the glacial period.
What a completely wild ride. Freeze, burn, freeze, burn. But out of all this climatic chaos, we finally enter the final stretch of our clock. The final era of the Precambrian, the Ediacaran.
Yes, the dawn of the animals, stretching from 635 down to 538.8 million years ago. The ice finally melts for good, the climate stabilizes, and suddenly the fossil record gets very, very weird.
These are the Ediacaran biota. I've seen pictures of these fossils while preparing for this deep dive. They look like, I don't know, quilted air mattresses, leaf fronds made of jelly.
That is actually a very common and accurate description. Organisms like Dickinsonia or Charnia, they were utterly bizarre by modern standards, completely soft-bodied. No skeletons, no hard shells, no teeth, no obvious heads or mouths.
Dickinsonia is the famous one, right? The flat oval with ridges.
Yes. Dickinsonia looked somewhat like a giant flattened fingerprint.
Yeah.
And they could get huge, sometimes a meter across.
A meter-wide flatworm thing, and they just sat there.
For the most part, yes. They were mostly sessile, stuck in place on the seafloor. They lived in what paleontologists call a mat ground ecology.
Mat ground.
The shallow seafloors at this time were entirely covered in incredibly thick, leathery, unbroken microbial mats. We often describe the fossilized texture left behind as elephant skin.
Wow.
These strange animals didn't burrow into the mud, and they mostly didn't swim. They just lay flat directly on top of the microbial mats, likely passively absorbing nutrients right through their bottom skin.
It sounds incredibly peaceful, honestly. No predators chasing you, no hiding, just living rugs soaking up a microbial soup all day?
It was a very tranquil period. We sometimes call it the Garden of Ediacara. But sustaining these large, complex, multi-celled bodies required a lot of energy. It required a steady supply of oxygen.
Right, because of aerobic respiration.
Exactly. And we see clear evidence of massive pulses of oceanic oxygenation throughout the Ediacaran period.
What caused the pulses?
We can track it through the nitrogen cycle in the rocks. The isotopes, specifically delta nitrogen-15, show that these oxygen pulses were tightly coupled with high nutrient availability.
So the vitamins came back.
Yes. The glaciers from the Snowball Earth had ground up mountains into fine dust. When they melted, they flushed an unbelievable amount of phosphorus and other critical nutrients into the oceans.
Huge fertilizer dump.
A massive fertilizer dump. This caused massive blooms of algae. The algae performed photosynthesis, creating oxygen. Then the algae died and sank, burying their carbon in the seafloor. This biological pump prevented the carbon from recombining with the oxygen, leaving a surplus of free oxygen in the water for the animals to use to grow huge.
So everything is great. The mats are thick, the animals are huge, the oxygen is flowing, but all good things must come to an end. In my outline, I see we call the violent end of this peaceful era worm world.
Yes, the agronomic revolution.
Which sounds like a polite farming convention, but I'm guessing it was actually total destruction.
It was absolute ecological devastation. It was the invention of deep burrowing, a process we call bioturbation.
Bugs digging in the mud.
Right. Entirely new, highly active, bilaterally symmetrical animals evolved. These were the true ancestors of modern worms, arthropods, and mollusks. And instead of just sitting politely on top of the mats, they evolved the musculature to actually dig violently down into the sediment.
They literally tore up the mats.
They absolutely shredded the microbial mats that the peaceful Ediacaran biota totally depended on for food and stability. They permanently turned the quiet, two-dimensional world of the flat seafloor surface into a chaotic, churned-up, three-dimensional world of muddy burrows.
They completely ruined the neighborhood.
It's a classic case of biotic replacement. The new engineers outcompeted the old ones.
And with worms moving around, I assume things started eating each other.
Yes. They brought active predation. The peaceful garden was over. Right at the very end of the Precambrian, we suddenly start seeing the very first hard skeletons in the fossil record. Tiny shell-like structures called clodina and another called namacalithus.
Because if you're taking the energy to build a hard calcium skeleton,
It usually means you are desperately trying not to be eaten by something else with teeth. An evolutionary arms race had officially begun.
So the peaceful garden rapidly becomes a heavily armored war zone.
A war zone, but a vastly more dynamic, complex ecosystem. And this exact moment, the appearance of hard parts, predators, and burrowers, this firmly sets the chaotic stage for the Cambrian explosion. The weird Ediacarans completely vanish from the fossil record, rapidly replaced by the highly mobile, burrowing, swimming, actively hunting animals that we eventually recognize as our own distant ancestors.
Incredible. So looking back at the clock, what does this all mean? We have journeyed from a literal magma ocean to a toxic orange smog world, to a frozen white ball of ice, to a peaceful garden of living rugs, to a worm-filled churning mud pit. What's the grand takeaway here?
If we connect all these disparate eras back to the bigger picture, the unifying theme is the deep co-evolution of Earth and life.
Coevolution.
Yes. We typically instinctively think of the physical environment as a static stage, and biology is just the actors performing on it. But in the Precambrian, the actors physically built the stage.
Life made the oxygen gas that turned the rocks red. Life made the methane haze that kept the planet from freezing early on. Life eventually cleared the sky.
Exactly. Life is a massive geological force. And the other vital takeaway is that crisis is the ultimate catalyst. The catastrophic oxygen holocaust, the apocalyptic snowball Earths, these were near total extinction events.
Almost ended the whole experiment.
But without them, we would almost certainly still be just a thin layer of bacterial slime on a rock. The intense, unbelievable pressure of those global disasters is exactly what forced the complex biological innovations. Eukaryotic cells, sexual reproduction, multicellular bodies that ultimately make us and everything you see around us possible.
It really makes you look at a simple blue sky entirely differently. It wasn't always just there. It was actively built, molecule by tiny molecule, by trillions of microscopic bacteria over billions of years.
It absolutely does. It's a constructed atmosphere.
Well, here is a final, slightly provocative thought for you to chew on as we wrap up. We, humanity, are constantly pointing our telescopes at the stars, desperately looking for life on other exoplanets. We specifically look for Earth-like planets, green and blue.
Right.
But for 88% of our own Earth's history, Earth-like meant a toxic orange haze, or a completely frozen ball of ice, or a stinky sulfidic ocean with zero complex life.
That is a profoundly important point. If an alien astronomer saw an orange Earth through their telescope right now, they might just dismiss it as a dead toxic world. But it might just be a vibrant Archean Earth teeming with microscopic life just waiting for its own Great Oxidation Event.
And maybe, just maybe, right now, we are currently in the middle of another massive planetary transition. We are rapidly changing the atmosphere again. We are actively changing the ocean chemistry.
We truly are. We have become a fundamental geological force, just like those simple cyanobacteria were 2.5 billion years ago. The ultimate question is, will our self-made transition be a deadly catastrophe or an evolutionary breakthrough?
That really is the defining question, isn't it? Well, thanks for taking this incredible deep dive into deep time with us.
It is always a pleasure to talk about the hidden history.
Keep looking up at the stars and keep looking down at the ancient rocks. You never know what wild story they are silently telling. Catch you next time.